All right, hopefully you've had a moment to figure out what the forces are going to be on this cart. And they may be surprising to you, but they're both down. It's the normal force because there's a contact point between the wheels of the cart and the track. And there's also gravity, which is down. They both have to be down. So you might argue, wow, that means the object is going to accelerate down. That's exactly what happens. The object is accelerating downward towards the center of the circle when it's at the top right here. So this is an example of the centripetal acceleration acting on the object and a centripetal force, which is the combination of the force of the contact force between the cart and the track and the force due to gravity, both pulling down on the cart at this point. So how do we apply Newton's second law and figure out what the acceleration is going to be and under what circumstances the object will stay on the cart? That's what my goal is, or the cart will stay on the track, I should say. That's what my goal is in doing this. So if I go on to the next slide, I'm going to apply Newton's second law in the vertical direction at the point that the cart is at the top of the track. So the y direction is positive up, the negative y direction is downward, the direction both of those vectors are pointing. So when I go here, I'll apply Newton's second law. I'll say, okay, the net force in the y direction is equal to the mass times the acceleration in the y direction. Then what I'll do is I'll say the acceleration, since it's downward, I'll put a negative sign in there to reflect the fact that acceleration is downward, just like gravity and normal force are. Everything has a minus sign in front of it. I can actually multiply everything by -1 to make it all positive, which I'll do, I think, on the subsequent slide. In order for the object to stay on the track, this is important, I'll just mention it right now since it's written there, the normal force has to be non-zero. It has to be greater than 0 for the object to stay on the track. Once the object leaves the track, the normal force is gone, and the object is then in free fall. We don't want that to happen. So, a couple of things I'll do. One is I'll replace the acceleration with v squared over r, and the other one, as I mentioned, is I'll multiply everything by -1. So the equation that we had earlier is now this, where acceleration is now given by the centripetal acceleration, v squared over r. And I will solve this equation for the normal force in the next slide. The normal force has to be greater than 0. And if that's the case, then the difference between mv squared over r and fg, which from this slide over here, all I'm doing is subtracting fg from both sides, leaving the equation being that the normal force is equal to mv squared over r minus fg. This has to be greater than 0. And of course, I can always substitute fg is equal to mg, making this equation even more understandable, because fg is just mg. So the difference between these two terms has to be greater than 0, as is shown in the next slide. That is the condition in which a roller coaster will stay on the track. The velocity at the top of the track has to be such that this condition is met. If we then solve for v, the m's cancel and we'll multiply by r and take the square root. This is the requirement for an object to stay on a track of a roller coaster based upon our understanding of Newton's second law and centripetal force and centripetal acceleration as we've just been introduced to it. If we did an example, what would be the minimum speed for a track of radius 10 meters at which a roller coaster would have to take or have to have at the top of the track in order for the roller coaster to stay on the track? Well, if we go to this equation here, I would put in 10 meters, and I'll take g to be 10. Square root of 100 is 10 meters per second. So the speed would have to be at least 10 meters per second at the top of the track in order for the roller coaster to stay on the track. Do the same thing for any radius. 20 meters per second, a bigger roller coaster. If I put in r is equal to 20 here, square root of 20 times 10 is the square root of 200. The speed has to be greater than the square root of 200, or greater than about 14 meters per second in order to stay on the track. Of course, if you were really designing a roller coaster, you'd want to make sure that your speed was comfortably above that amount. You don't want to just make it across the top of the track. You want it to be greater than that. Next thing I'm going to talk about is whether somebody who's standing at the equator, which is what this person represents, or somebody who's standing at the pole, which is what that person represents, which does their location at which they're standing affect their apparent weight. And we're going to use the calculation we made a couple of videos ago for the speed of an object moving around the equator being 465 meters per second. And the speed of a person at the pole is effectively 0 meters per second, because they're moving in 24 hours, they're spinning once. In this case, in 24 hours, they're going around the Earth once if they're just standing at the equator. So let's see what the effect of that is, and that's something I will do on the next video.